Hi, my name is Jordan Velde. Welcome to my Physics Lab 1 Constant Velocity. For this lab, I will be analyzing the horizontal motion of an object moving at constant velocity and creating a computational model in two position versus time graphs using my data. For this lab, for the object, I used a dry erase marker. To observe the observed position, I used the tracker app. And to create my computational model and the expected position graph, I used GlowScript. The purpose of this lab is to compare the observed position of an object moving at a constant velocity to its predicted position using a computational model. An overview of the results include displaying a linear relationship between displacement and time, which helps explain Newton's second law. Both position versus time graphs displayed similar lines with small differences between them, which could be due to possible human or experimental errors. The principles used in this lab include Newton's second law, also known as the momentum principle, which states that the force on an object equals the rate of change in its momentum with respect to time. Looking at these formulas, we can see that if the net force equals 0, then the change in momentum must also be 0. If the change in momentum equals 0, then the change in velocity must also be 0. Using the velocity update formula, we can see the same relationships. If the net force equals 0, then the velocity update formula shows us that the initial velocity equals the final velocity, meaning it is constant. A few lab details. The system for my lab was the dry erase marker. The surroundings were everything else. A few assumptions that were made was that the net force on the object is 0 and that the system is moving at a constant velocity throughout the tracking period. The procedure for this lab included recording a video of the marker moving across the screen in a straight line. Then I used the tracker app to track the ball's observed position frame by frame using a set time period. Then we used GlowScript and the given starter code to create a computational model that will predict the marker's position. Then I used an Excel spreadsheet to record the data and create a graph that compared the observed position to the marker to the predicted position. For the observations made during the lab, starting with the initial conditions shown on the screen, I imported the video that we filmed of the marker moving across the screen to the tracker app. I used the coordinate axis to make the x-axis parallel to the table. I then set a calibration stick of 1 meter that was aligned with the meter stick that we used in the background of our video. I used the tracker feature to track the center of mass for each time frame, which was about 0.03 seconds each, and I recorded each position on a Google spreadsheet. To make the computational model on the GlowScript app, I made edits to the given starter code in GlowScript to create the computational model used to predict the position of the object. The mass of the object did not affect the graph, and I input our initial position and velocity. I set the delta t to 0.03 seconds, since our frames were 0.03 seconds each, and I set the final time to be 2.87 seconds, since that was the last recorded time. Here are pictures of the starting code that we were given, and the final code that I used for the computational model. The arrows show where I made the changes in the code, as said before, including the ball's position, the ball's velocity, and the final time, as well as the delta t. Here is what the code showed after we ran it, including the position versus time graph. The results of this lab, to the right, as you can see, the graph that compared both the observed position versus time graph and the predicted versus time graph were put into a singular graph as shown on the right. The blue line represents the observed position versus time graph, and the red line represents the predicted position versus time graph. As you can see, the two lines look very similar, having similar looking slopes. However, small differences can be seen as the blue line is not perfectly linear while the red line is. Regardless, both show a positive linear relationship between displacement and time. Possible sources of error could have included the frictional force. For the observed position, we assume that there was no forces acting against the object's horizontal motion. However, there is the force of friction. The computational model accounts for this because we set the net force equal to 0, which is why it's perfectly linear, and the one for the observed position is not. Also, for the center of mass, there could have been human error when tracking the position of the object, since we had to click on the object's center of mass each time, which could have changed between frames. In the computational model, this stays constant. Follow-up questions for the lab, including, if we change the axes, how would this change our results? For the graphs, the slopes of the graphs would have been similar but opposite. Instead of being constant in the positive direction, it would have been constant in the negative direction. What does this mean? Is it possible for us to say how many pushes and pulls are being added together to give zero net force in the case that you observed? No, it is impossible to say exactly what forces are pushing and pulling on the objects, since they are all balanced out in the computational model when we set the net force equal to 0. Because of this, we are not shown what forces are acting on the object and their magnitudes. However, we know that the likely forces include gravity, friction, and the normal force from the table.